Hi guys, it's Chandler. I saw that someone asked for help with this problem in the group me, so I'm gonna show you guys how I got through it and hope that that helps. If you have questions, obviously ask. Okay, so basically where I started with this one, if you look at like A and B, they're both blank. It's really hard to start working right there because, like, I don't know how to explain, like, there's no way you would know what's happening. So I started here. So what does this tell us? There's like good info in here. This like reagent combination shows us that there's going to be a terminal alkyne. So that's important. Like, one, you can see that there's some sort of alkyne, probably because like deductive reasoning, but if we have 3 equivalents of sodium amide and some sort of like a water workup, we know we're going to have a terminal alkyne in here. So that's really helpful. So essentially what this whole like A to C is then is creating a terminal alkyne from an alkene. And how we learned how to do that in class is the dehydrohalogenation. I may have butchered that, just pretend I didn't. So essentially how that works is we're going to take this alkene, we're going to create essentially an alkane chain that has halide groups with hydrogens, so technically hydrides, I guess. And then we're going to create a triple bond from there, and then that's our whole process. I'm going to draw this out, so I know it sounds like I smoke crack for a living. I'm sorry. I'm trying my best. Okay, so without further ado, let's get started, I guess. So this is kind of, I guess I'll show you here. So this is kind of like where I'm going to be writing stuff out, and then we can put our answers in these boxes. So, like I said, let me see. I'm trying to get this so you guys can see, but it's a little rough, not gonna lie. Okay, so is that it? Question mark? Maybe? Okay. So, like I said, we know that we're gonna need to create an alkyne here, and we know that we're gonna need to make a like group with halides and hydrides on it. So the best way to do that is to use Br2 and CH2Cl2. Hopefully you can see what that says. I don't know. I know it's a little hard, but I'm saying it, so it's okay. And then I'm going to show the mechanism below for that. Hopefully that clears up any confusion. Obviously, if you have questions, just ask too. So we're going to have our alkene, and there are 2 BRs. And then we know, like from class, I guess, that the alkene will be the nucleophile. And it's going to attack this bromine, which will actually come back and attack here. And this bromine will leave. So that creates the bromonium bridge. Also, this isn't like the best depiction of what's actually happening, because she said that we don't have to include stereochem. So like when I was doing it, I didn't really think about that. So obviously we know there's going to be anti-addition, but in the exam, like, we don't have a lot of time for this, so it's kind of get it and get out sort of thing. So we know that this group will attack our most substituted carbon, and then those electrons will be donated back to this bromine. So this is our answer for part B. I'm going to draw it better. It's a little janky looking, but so we have this. That's BR. Okay. And then, so from there, we can use the reagent she gave us to create our terminal alkyne that I talked about earlier. So that's like kind of like part 1 or whatever, I guess. So we'll draw like a little line. So we'll go here. Sorry if I say 40,000 times. So with the sodium amide in solution, I'm not going to include the sodium or the NH3 just because we kind of know that that is, like, the NH3s are solvent and the sodium's just dissolved in there, so they're like all spectator species. Keep in the back of your mind they're in there. But again, like, so she didn't ask for the mechanism, so I didn't include all of that. And if there are questions, just ask them in the group me. Ooh, my roommates just got home. Fun. They might come say hello. I don't know. So anyway, we have our sodium amide. This is our first equivalent of the sodium amide. So, okay, can you see it? Yeah, so our first equivalent, also I'm going to show the H's because that's kind of crucial. So we can see each carbon has 4 bonds, 1, 2, 3, 4, 1, 2, 3, 4. And that consists of the halides and the hydride, which are just their H's with the electrons. So this amide group is going to attack hydrogen. I'm gonna actually do this one because it's just easier to see. And then the electrons will go to make a pi bond. And then since this carbon would have 5 bonds, essentially this bromine group will leave, so to make that possible. And from my understanding, when we were doing it in class, if you have 2 of the same halide, it doesn't really matter what side you attack first, because I know you'll get the same product, especially if you're not depicting stereochem. So, yeah. But there may be need for clarification with that. And then, so let's think about what just happened. So, this bromine group left. So, it's like spectating. I'll show it. There's still a hydrogen here. And now we have a double bond. This hydrogen went to go make the double bond, so it's gone. And then one thing I always like to do when I'm kind of doing these reactions, I always check the carbons I'm interacting with to make sure they still have 4 bonds, just to make sure you're not losing things, adding things, whatever. So 1, 2, 3, 4, 1, 2, 3, 4. All right, so we're good to continue with our second equivalent of sodium amide. So here, I like to write second equivalent, kind of helps me visualize, because, you know, we get 3. Also, that might help you guys. So, yeah. So, we always attack the side opposite of the halide that we're trying to get rid of. So, I'm trying to think of the best way to draw this so you can see what's happening. Hopefully this makes sense. And then, since this would then have 5 bonds, this bromine leaves. So now what's actually happened is we have made our alkyne. I'm going to kind of draw it in the funny looking manner it would be with an improper bond angle, so I can show you guys how it's going to be in true form, I guess. That was incoherent, but whatever. We'll just pretend it wasn't. So these are, and this bromine's also gone, so like just imagine these are out here. Imagine that they have their electrons around them. I don't feel like drawing them. So this is the same carbon. That is not natural. That is not a proper bond angle. So we're going to fix it so it looks correct. So that's what it actually looks like. And then from, shaky. Then from there, you probably saw we still have 1 equivalent of sodium amide left and hydronium. I'm pretty sure that's what it's called. If not, just pretend I didn't say that. So essentially, we're going to use our third equivalent of sodium amide to deprotonate and reprotonate. And like Dr. Peterson said in class, it's not really that you want it to happen, it's more that you can't prevent this from happening, so we need to depict that it's happening and then reprotonate with some sort of group. In this example, it's going to be the hydronium. So there's not really a great point to this, but we know that it happens. So here, and then this hydrogen here is gone. Oh wait, that's an NH2, sorry. I'll be making an NH3. And so this forms a carbanion ion. Hopefully this makes sense. I didn't really explain it that well. If you have questions, ask. So then we're going to use our hydronium that she told us will be here. Alright. And then we know this will attack, form the water, and this will reprotonate to give us our desired product. Technically, when you're looking at the products, they're going to be the same, so if you have it in your head when you're doing this problem, like, oh, okay, I see 3 equivalents of sodium amide, a solvent, which is our NH3, and a like water workup group, and you don't want to draw the mechanism, that's a great way to save time because you know it's just going to deprotonate, reprotonate. But I mean, I just wanted to demonstrate in case there was confusion about that. So this is going to be our answer for part C. That's our terminal alkyne. So if you look, you can basically see that in part D, we're going to add something that's going to replace this hydrogen area with a carbon chain. So the easiest way to do that is actually to just create another carbanion, which sounds counterintuitive because we just did that. But then we're going to add the carbon chain because that is the only way to extend our carbon. So let's go ahead and do that. I'm going to draw a little line. This is starting to get hard to look at. I'm sorry. I'm trying my hardest. I really am. So these are what we like have. I'm not going to draw the water because it's just like spectating at this point. And then in the corner, I'll kind of like write what I'm using for reagents so we can just easily put that in the box for the answer. So like I just said, we're going to use another sodium amide. And then we'll just put the NH3 with that because that's the solvent that we use when we do that. And her key says that too, so that's how you know it's right. So, from there, oh, I just realized these both say NH3. I'm really sorry. They're NH2s. Apparently I'm illiterate. You should, like, I'm sorry. That's unfortunate. Hopefully you're not like, oh, she's dumb. Sorry. But yeah, so we're going to take our next sodium amide. Attack, create our carbanion, and then we can go from there. Alright, so see, like, that makes NH3 now, so it's spectating. These are NH2s, don't be dumb. Or at least know that it's an N that has 2 electron groups and negative formal charge, because realistically it doesn't matter that much when she's not asking for the mechanism. But yeah, don't make the same mistakes I've made. Okay, so let's take a look. We have our terminal alkyne and our internal alkyne. So we need to add this part. So I don't know if you guys remember in class, you probably do, maybe not, but the easiest way to add a carbon chain is to have a carbon chain with a halide on it because the halide carbon bond is not that great. So like it's gonna easily become unattached. I'm gonna demonstrate that better now. So this will be our next part of our reagent. You can see it right here. So when you have a highly electronegative atom like bromine, it's actually going to be kind of hogging all of the electrons that these are sharing. So there's actually a temporary dipole in here. Well, I don't know if temporary dipole is the proper word, but the bromine's hogging the electrons, and you just need to understand that. So there's a partial negative here and a partial positive here. So essentially the carbanion can go attack this partial positive group, and then this bromine will leave with those extra electrons. So that will give us, so you can see we're here, we're adding this, and there's going to be a spectator bromine now. And that's just from here. And there are also many other spectators in the solution that we talked about earlier. So now you can see this is the same as this. So that's our answer. So for this part, let me see, hopefully. For this part, I think that you're okay to just draw the line angle because, oh, that's a 2 again. Sorry. You're okay to draw the line angle because I was like skeptical about doing it, but then that's what it says on her key. So like, that's how you know it's okay, because if you try to go for like all the CH2, CH3, all that garbage, like say she wants more than just this, I think it's easy to mess it up, and if it's on her key, she's okay with that. So she said we can skip part E, because I think it's something we haven't done in class. So now we just need to know how to get from this to this. So there are certain things that we want to be observing when we're looking at this. I'm sorry that this whole thing looks so janky. This is like rough, but hopefully you get the idea. So we're going to have an alkene, and we're going to syn add 2 oxygen groups. I don't know if you guys remember from class, but it's like the syn-diol, like 2 alls, like 2 alcohol groups. I think they're technically called hydroxyl groups, but I can't name. Anyway, so there's really only one reaction that'll do syn-diols, because I know, like, obviously hydroboration will do syn H and OH, and that makes an anti-mark product, so like that, I mean, technically you can see that here, but it's not what we're going for. So if you want to have a syn-diol addition, that is with the osmium tetroxide, and then the H2O2 and H2O, and that's kind of just something that you have to remember from the lecture, because we kind of went over the mechanism a little bit for this one, but there's only one way to add 2 syn-diols. It's that. It's from lecture 18, actually, if you want to go take a better look at that, because like, to show you like how it works, we'd have to just do the whole mechanism like right here, right now. We did it in class. But if you have any questions, obviously ask. Hopefully that has been helpful, and if there's any confusion or anything, just let me know, or notes. Obviously, please don't tell me that they're amide groups, because I know. I'm just stupid. Alrighty, thank you guys. Have a good night.